And here is the ground underneath this vegetation patch is actually sloping sideways, and this makes it difficult for the robot to walk. And the robot cannot completely see it, and even then it is able to cross this. This is a construction site right in front of my house, and I took the robot and I made it walk down this mud pile. And we see that the ground is constantly moving and deforming, and the footholds are not stable at all, and the robot does the job well. Similarly, here are two more examples of unstable or damp ground. And we see that the feet of the robot in the top video get stuck once in a while, but it is able to get its feet out and continue walking. And similarly, when it is walking on the sand, the surface constantly deforms, but it is able to continue walking stably. So all the videos that I have presented and will present are from the same policy, which was trained without any real world samples and was deployed without any calibration or fine tuning. And the experiments that I'm going to show were spread over 2 weeks. And during this, there was some damage to the foot contact sensors. And we see that our robot is able to perform well despite this damage to the foot contact sensor. So now let's get into the details of our method. So we're going to learn how to walk entirely in simulation and entirely only on this terrain that you see on the left. But what we are also additionally going to learn is how do we adapt to situations that the robot has not seen before. So how does it generalize to all of this? And let me flesh out each of these in sequence. So let's first solve the problem of walking in simulation. So one simple way of setting this problem up is that I have a base policy, which is in the center, and I'm going to train this policy to walk. So the setup that I will have is that the policy takes as input the state of the robot. So these are the joint angles, joint velocities, the IMU readings and everything. And it is going to take an action, which is going to be the target joint angles. And then that will be fed into a physics simulation. And then the robot and the physics simulation will execute that action. And the base policy is going to learn by using trial and error or a zero order search method. We use reinforcement learning in our work to train this end to end. So, but what we are going for is actually something quite difficult. What we want is for our robot to be able to not just walk in one setting, but to be walk for all different settings of mass or payload. The center of mass might be different, the friction can change, the terrain height can be different, the motor strength, one of the motors can be weak, and so on. And we want our robot to actually be able to handle all of these. So, but what in the current setup that you see right now, we are expecting the base policy to learn a single way to walk, which works for all of this, which is a very hard problem. But what we want is something simpler. So we will feed this into the base policy because we want our base policy to know what it is dealing with instead of just being blind to what it is dealing with. So the base policy will take all the environment parameters, which are mass, center of mass, friction, terrain height, motor strength, and it is going to compress it into a vector of extrinsics. And this extrinsics vector, which is 8-dimensional for us, this 8-dimensional vector is what the base policy is going to see along with the state of the robot. So the base policy has two things. It has the state of the robot, and then it has some estimate of the environment. And now we will train this end to end, and now we will have a base policy which can work in all of these different setups. So we train this entire setting end to end using PPO, which is an on policy reinforcement learning algorithm. We train it with 1 billion samples, which takes 24 hours on a regular desktop machine. But importantly, all our reward terms are motivated from biomechanics and energetics. So we primarily optimize the physical work done and the ground impact as the robot walks. And there are some other terms as well, which ensure that the motions are smooth. And along with this, we also have a task reward. So we want the robot to move forward with a fixed speed. So these are the things. And then along with this, we additionally have this fractal terrain that you see on the right. So this fractal terrain is a way to generate natural landscapes. So we only train the robot on this terrain, and all the videos that you saw before, it has never seen them in simulation. So we train this end to end, and then we get the nice looking gate that you see on the right. Now let's try to deploy it. But the moment we try to do it, we notice that there is one big problem. We don't know what the exact payload or the center of mass or the friction of the ground or any of these are in the real world. So we don't know the extrinsics which the base policy needs to be able to work. Now, this is what people call the simulation to real gap. But the problem is actually slightly deeper than that. So if you think about it, even if I could measure the friction, the terrain, and all of these in my living room and compute the extrinsic vector for my living room, my robot would fail to walk in any of the setups I showed earlier. So instead of just going to my living room and estimating all of these parameters, what we are going to do instead is that we are going to estimate this extrinsic vector online at runtime. Now the question is, how do we do this? And the key idea we are going to use is that we are going to do it from proprioception. So we can look at the history of the states of the robot. So we can look at how the leg moved and we can try to estimate these extrinsics. But why should this even be possible? So if you think about it, if let's say I'm walking on a sand and my feet sink in deeper than I expected it to, then I know that I'm walking on a deformable surface. Similarly, if you're walking on a slippery surface and the feet move further than you expected them to, you know that the surface is unstable or slippery. And this information can be predicted just by looking at your own motion. And this is the signal that we're going to exploit. So now the next question to answer is that how do we train this? So we will go back in simulation. So we will go back in simulation, and the top row is the phase 1, which was already trained. What we really care about right now is this phase 2, the green box that you see on the bottom left. This is what we want to train in the second phase. So the adaptation module will go from the history of the robot to this extrinsic vector. But in simulation, we have both. At any point of time, we can use the phase 1 model to actually compute this extrinsics or ZT. So we can use that to compute the ground truth ZT at any point. And we know the history of the robot because we're in simulation. And then we can cast this as a simple regression problem and solve it using supervised learning. And now our policy is ready for deployment. So we will only take the second phase that we trained, which is the base policy and the adaptation module. And we are going to deploy it on the robot. And when we did deploy it on the robot, we found that the adaptation module was only able to run at 10 Hertz on the limited onboard compute. And the base policy was running at 100 Hertz. So this discrepancy, we did not train for this discrepancy, but when we deployed it, it did not affect our performance because the adaptation module, which is estimating the extrinsics, is changing very infrequently. And even if you are predicting 10 times a second, that rate is good enough for our algorithm to perform well. So we did not need any synchronization or calibration while putting it on the real robot. So do people have any questions? By the way, just feel free to unmute yourself and interrupt if you have any questions. Okay, so all right, so now that we have this, let's test it on some indoor setups. So this is my living room and I scattered some planks in my living room and they're loose and they move around. Now let's get the robot to walk across this. You see that as the robot walks, some of the planks are unstable and some of them move along with the robot as well. And these kinds of events actually throw up some of the classical estimators which run on the robot, but we don't use any of them. And you see that our robot maintains stability. This is my bed and this is my mattress, and I just put the robot on it to see if it can cross the mattress. And we see that it is successfully able to do it, even though it has never seen a deformable mattress before in simulation. And we also compared with evaluated it all across my house. So there's a slippery surface, there is a foam on which the robot walks, there's a stepping down task and stepping up task and so on. And we see that the robot was able to successfully do all of these tasks. Now let's get into some comparisons. So let's compare with the A1's built-in controller that ships with the A1 robot. So this is the first task. So in this, the robot has to step down this height and focus on the feet of the robot. And you'll see that when it walks, the moment it has a misplaced step, it destabilizes. But RMA will have the same misplaced step, but it will be able to successfully cross it. Here, the task is to go up this and notice the feet of the robot. It keeps the step on the edge and then destabilizes. But RMA will also struggle at the same edge, but will adapt online and continue walking forward by raising its leg higher. This is a foam. So both these algorithms have never seen foam before, or they weren't tuned on foam. And we see that the moment we start this, the built-in controller destabilizes instantly, but RMA is able to cross the entire foam path successfully. We can do another comparison. So we can take RMA and we can make the adaptation module make one prediction in the first time step and then switch it off. So we use that extrinsics for the rest of the episode for prediction. And this experiment will give us a sense of how important the adaptation module is for the system to work. So I'll first play the RMA video. So this is an 8 kg payload. The manufacturer comes with a 3 kg payload limit, and the weight of the robot is 12 kg. So this is roughly 70% of the weight. And when we switch off the adaptation module, you see that it struggles because the center of mass has changed, because the weight of the robot in the front, the weight is slightly uneven and it's more tilted towards the front, and that gets to the robot. We can also do the same foam comparison where RMA we know is able to walk on foam, but what if we switch off the adaptation module and we see that the moment the foam becomes slightly uneven, it actually fails to walk. Let's get into the working and details of the adaptation module. So here, this is again my living room. I spread out a plastic sheet and then I'll pour some oil on this. And now I'll ask the robot to cross it, but with the additional difficulty of plastic covering on its feet. So this will make the robot slip even more, and let's see how it does. So we see that it crosses this successfully, but let's see this in a slower motion. So if we see it in a slower motion, see that the robot slips, but then it recovers and then continues walking with a stable gait. And we can analyze this in more detail. So we can have 3 plots to analyze this. The top plot is the gait plot. So for each feet, when it touches the ground, you see a dark color, and when it's missing, it's not touching the ground. So we have 4 lines, one for each foot. And then we have the knee torque. So this is the front right knee, and we just plot the torque profile of that. And the last plot shows 2 out of the 8 extrinsics values. So the extrinsics is the 8-dimensional vector. We pick 2 values which changed the most, and we just plot them. And we see that when I run this, you will notice that the moment the robot starts slipping, the extrinsics vector captures that fact and continues capturing it. And that is what enables the torque and the gait pattern to go back to normal. Note that the robot entered the slippery surface before, but it captures that it is slippery only when it actually started slipping, because that's the only signal the robot has. We can do another test where I toss this 5 kg payload on the back of the robot, and we see that the robot is able to walk. And let's play this in a slightly slower motion and focus on the 3 green dots that you see in the center of the robot. When we throw it, the robot actually takes a hit, goes down, continues walking for some time, and then it tries to get back up here. And we can analyze this with the same 3 plots. And we see that when the payload lands on the back of the robot, the knee torque goes up, the steps become more frequent. But the moment the extrinsics change to capture the fact that there is a payload on the back of the robot, the gait plot and the knee torque go back to normal. Now let's talk about some related work in legged locomotion. So legged locomotion is a very old problem, and there have been several hardware and software solutions proposed for this. In fact, Cord Lab at UPenn is one of the world experts in building some of the most stable solutions out there. There has also been a large line of work on using learning for locomotion, where they use a data-driven approach to learn how to walk. And they've also shown some quite impressive results in difficult terrain. And there are 2 ways to get to learning for locomotion. You can either train in the real world itself, or you can train in simulation and then go in and then transfer to the real world. The problem with training in the real world is that for difficult setups like a very rocky surface or an oily surface, it's very dangerous for the hardware to train on those setups. That is what has motivated a long line of sim to real work for locomotion, in which case there is some form of simulation calibration, where you look at the simulation, you try to calibrate it and make it close to the real world, and then you show a sim to real performance. And lastly, this is the approach we take, which is that we combine sim to real and real to real adaptation in one single framework. And for adaptation, the existing methods which fine tune at test time or in the real world, they take up to several minutes to adapt, whereas our method does it in fractions of a second. We can more quantitatively compare it to the baselines. So I'm going to compare to three classes of method. The first is domain randomization, where we train a policy which is blind to what it is dealing with. It does not know what it is dealing with and doesn't even estimate that. So now it is overly conservative because it is trying to learn a single policy for all of these, and that reflects in the performance. The second method is system identification. So instead of estimating this extrinsics, we can also estimate the exact center of mass, the value of mass, friction, etc. And we can see how well does the robot perform. And we see that even in this setup, it's solving a harder task than necessary. You don't need to know the exact value of friction to figure out how to correct for it. And the last set of methods are the ones which are going to fine tune at test time, and they takes up to several minutes to adapt. So we compare to all of these methods and we see that we have a much higher success rate, and we are also have a smoother torque and jerk profile, and our motions are much smoother compared to all these baseline methods. We also compare to RMA in the real world and indoor setups with two baselines. So the first baseline is the built-in A1 controller, and the second one is the RMA controller, but without the adaptation module. So I make prediction for the first time step, and then I freeze the adaptation module and use the same extrinsics for the rest of the run. So we see that RMA matches or outperforms all of the baseline methods. The A1 controller also does pretty well in some situations, such as walking upward on the incline or walking on the mattress. But we see that there are several other situations where it fails to adapt or very quickly destabilizes. Okay, so what's really exciting about RMA? So the most important thing is that it actually works on real hardware, and we have tested it extensively. But if we let's take a closer look at its technique. So there are three things in the technique which I find to be quite interesting. So the first is that we don't use any hand-coded prior or any heuristic control stack that we predefine for the learning task. The second is that we show generalization to terrain, which is beyond what it has seen in training. And lastly, we have an asynchronous design, which allows us to seamlessly move to a low compute without any calibration or synchronization problems. Now let's look at some of the emergent behavior we get because of this, because of not hand coding any priors or leg movements. So this is the first video that I showed in the talk. So in this, the robot is trying to walk on between these rocks, and we see that its feet get stuck and then it tries to get out of it. But let's take a closer and slower look and look at all 4 feet of the robot. When the robot gets stuck, instead of following a predefined trajectory, all 4 legs stop. And when the front legs adapt to this obstacle and get over it, we see that the rear legs right now will also start walking. Another example of this is an indoor. We see that the robot will get stuck and then we'll try to cross it and then continue walking. Okay, so we saw the practical benefit of emergence of this obstacle avoidance behavior if we don't use any predefined foot motions or leg trajectories or a heuristic control stack. But apart from the practical benefits, one of the main reasons why we did not include a hand-coded prior or predefined leg trajectory is our inspiration from how locomotion develops in babies. So Karen Adolph is a professor at NYU, and she studies how babies learn to walk. And in one of her papers, she makes a distinction between natural locomotion of freeform walking and a gait-centered walking or straight path walking in labs, which is centered on classifying walking into gaits. So on the left part of the image, you see the step width, length, periodicity. All of these are used to define a gait. But on the right, what you see is the path that a baby takes when you let the baby walk freely in a room. The baby starts and stops arbitrarily and violates several periodicity assumptions. So this is definitely true, and we do know that this is definite, but this is not the complete picture, because we also know that horses and dogs show several different gaits. So we know that they have the walk gait or the trot gait where the alternate legs are in sync, or a gallop or run gait where they have a short flight phase, and so on. And this is not specific to animals like dogs and horses. This is seen, this periodicity or regularity of gait is actually seen across a huge number of, large number of quadrupeds in nature. And we can even generalize this to animals which are not quadrupeds. So we see that even snake, grasshoppers, and birds have this periodicity. Even a snake has some periodicity and repetition when it is trying to walk. And once this idea of gaits was around, there was interest in computationally defining it and understanding how the gaits relate to the velocity. So we have we have this camp. So now let's take a step back. So we have seen two behaviors. The first is, we know that babies walk in bouts of steps in complex terrains, but we also know that animals show structured behavior on simple terrains. So how is there a scientific way to reconcile both of them under a single framework? So we will take the learning by, so we'll take the analysis by synthesis approach, and we are going to, so we're going to take an analysis of synthesis approach to actually show this hypothesis. But before we do that, let's look at the biomechanics literature, because researchers in that field have actually studied this for quite a while, and they've proposed several hypotheses. And the top left hypothesis, which is the energy hypothesis, is our most favorite one. And what they did in this experiment is that they took a horse and they asked the horse to walk at different speeds. And they measured the oxygen that the horse consumed while walking. And this is a plot that you see. So the plot has two things. So the y-axis is how much energy is consumed. The x-axis is the speed. But the different curves you see are also the different gaits. So on top of this, they were also keeping a note of which gait the horse is using at what speed. And then you see this curve. And this motivates our hypothesis, which is that minimizing energy consumption leads to emergence of gaits in legged robots. So we are going to take a synthesis approach. So we'll have the same simulation setup as before. And the only thing that we are going to change from that is that we are going to add different target speeds. The results that I've shown up until now were from a same fixed speed, but now we're going to change a different target speed to see what happens. So we're going to minimize the physical energy, which is shown on the bottom left. And our algorithm is just going to predict the target joint angles at 100 Hertz, and it knows nothing about gaits. And we will just see what happens at each of these speeds. So this is the gait it gets to at low speed, and this is a walk gait. So it's walking from grass to concrete. This is almost, in this gait, the alternate the diagonal legs are almost in sync, but are slightly off. We can take it to a higher speed. And we see that it converges to a trot gait. So the diagonal legs are roughly in sync. So note that our algorithm doesn't know about these gaits. It's just making predictions at 100 Hertz to walk efficiently at each of these speeds. And at even higher speed, we get to we can take it to an even higher speed, and we see that it gets to this bounce gate, which has a small flight phase. And let me play this in slower motion so that the flight phase is visible. So the flight phase is when all 4 feet are off the ground, and we see that our algorithm converges to this flight phase for efficiency at high speeds. So we show all 3 speeds next to the gait plots. So the dark color in the gait means that the feet is touching the ground, and the light color means that it's off the ground. And if we look at the gait plots, we see that we have the walk gait at slow speed. In the trot gait, the alternate feet are roughly in sync. They're not exactly in sync, again, because we don't build in any gaits. And once we get to the bounce, the high speed walking, we see that there are vertical lines or vertical parts where none of the 4 feet are on the ground, and it has found a flight phase, which is used to walk. This is a fun comparison to how dogs walk. This is at a very low speed at just 0.35 meters per second, and we can see that both of them have similar gaits, and this is at a slightly higher speed. So I just place them next to each other just for fun to see how it appears when visually compared. But we can do a more quantitative comparison. So there's a number called the Froude number, which is used to compare different animals in biology. So in biology, if different animals have same morphology but different heights and are walking at different speeds, you can compute a number corresponding to it, which is the Froude number. And animals with the same Froude number should take the same gait, should be walking at the same gait. So we treated our quadruped robot as an animal, and then we added a column to this, and that's the robot A1. And we see that it is actually quite similar to sheep and horses in its Froude number. So although everyone thinks that the quadruped robot is actually a dog, but we found that it is closer to sheep and horses. Now we tried recreating this similar plot. So the trends look roughly similar between the two. What we plot is slightly different from the original horse paper. What we plot is the physical energy consumed to walk, and we force the robot to walk at each of the different speeds using different gaits. So we force the robot to take the walk gait while walking from a certain speed range, and then we force the robot to take a trot gait by walking in a different speed regime. And similarly, we force it to take a bounce gait. And the stars that you see, which are overlaid on the top, is what our algorithm discovers in that speed. So we see that our algorithm is discovering our learning framework automatically latches onto the right gait at the right speed. Now let me show you some more robustness tests. So since these are higher speed gaits, let's see if they're also robust when we test them in the real world. So this is the trot gait. It is going down the trench and then goes back up. See that it accelerates slightly and then slows down slightly. Similarly, we can add a 1 kg payload to the trot gait, which is 3 times faster than what we were walking with before. And here we force it to walk through a bush, and we see that it gets destabilized but continues walking. Similarly, we can take our highest speed gait, which is 5 times faster than what we had before, and we see that it is able to walk through this. We also abruptly we pulled the robot to the left, and we lifted the robot and tried disturbing it while it's walking at 1.5 meters per second, and we see that it maintains stability. Now let me just slow it down once. You see that the operator will pull it to the left, and then the robot recovers from that. And at the end, when we pull it up, it starts flailing its legs to get back on the ground. So now it's no longer using any notion of gait anymore. The moment it sees a slightly different condition, it switches to non-periodic behavior, which is what we should expect. Now that we have 3 policies which can walk at 3 different gaits, we can also distill them into one policy using supervised learning. So we have a supervisor or a teacher which knows how to walk in each of the 3 different speeds, and we can distill that into a single policy. And we can get this kind of a behavior where now we have a policy, and all we need to do is to give it a target velocity, and then it walks at that. It automatically switches to the right gait, figures out what the right gait is, and continues walking. We can see all of these gait transitions in a slower motion. And we see that they're also smooth. So there isn't like a very abrupt jump when they try to change the gait. And all the operator needs to do is to tell the robot how fast the robot is supposed to walk. Okay, so we have seen the structured gait in simple terrains from our energy minimizing framework. But can we explain the bouts of step we saw in babies when they walk? Can we explain this behavior of unstructured locomotion or gait-free behavior of natural locomotion when it is not in a simple setup? So we take the same framework, we are minimizing energy, but we make the terrain more complex. So you see that the fractal terrain, the terrain is more sharper and higher, and the robot now learns to walk on that at some fixed speed. And now what we are going to do is we're just going to deploy it in the wild. Yeah, so now what we're going to do is we make it run across this plank, the sequence of planks, and we will observe, and I'll plot the gait just below it. So the dark color means that the feet is in contact, and the light color means that it is not. And we can observe, and we will observe that it is actually not following any specific gait every time it comes next to an obstacle. So the gait patterns are very frequently violated in this region, every time it faces something which is not flat. And this is, I think, the hypothesis. This completes my analysis. So now we have the same framework, which is able to show different gaits at different speed. And the moment there is something which is not expected, instead of still trying to explain that through gaits, it latches onto an unstructured walking behavior. Okay.
Ashish, I think there's a question. Is there a question?
Yeah, I have a question. So, in the adaptation module, are you so while training in simulation and then doing the adaptation, when you do the adaptation, does it have some notion of memory to remember which terrain it has seen, or every time it sees a new terrain, every time it sees a terrain, it just treats it as something new and tries to learn online?
So it has so the base, so we have a base policy. 1 second, let me switch to that. Okay, so this is the final policy we deploy. So the base policy does not have a history. It only looks at the current state and action. But the base policy does get to look at some memory through this adaptation module. So we look at the history, that 50 time steps, which is half a second of history at every time step, and then we try to make a prediction. So the base policy has some memory, but that memory is bottlenecked through 8 dimensions, or this ZT.
Okay.
But an extreme version of memory would be if you use a recurrence or something which can maintain a very long-term memories. But we don't have that.
Okay, cool.
Yeah, so just to clarify for questions, so there's a mic in this room, so she should be able to hear you. And people on the Zoom call. So there's apparently no Q&A, no window or no chat, but you can just, I don't know, raise your hand on Zoom, or I don't know what Ashish you're comfortable with.
I think just unmute and interrupt. I think I'm okay with that.
I had a quick follow-up question to the last one. So I think you said it had half a second, but my assumption was that it was more like 5 seconds at 10 hertz. So maybe I'm just doing something wrong there. But the question, and would apply either way, was whether in that first half second or 5 seconds you see the robot more likely to fall.
I see. So so we are collecting observations at 100 hertz, and it is 50 time steps. So each time step is essentially from this 100 hertz. So we're collecting the state of the robot at 100. So 50 amounts to half a second. But the adaptation module works on a rolling window. So it works on a moving window. So at every point in time, it looks at half a second in the past, whatever that half a second is, and makes a prediction. And that it does 10 times a second.
Got you. Great. So I guess, yeah, did you get to see whether, in the first 5 seconds, then before the adaptation module has, I guess after 5 seconds, if it's staying on the same terrain, it's kind of done adapting, although I guess the terrain is changing too. So yeah, I just wondering about when it goes.
So there is some very small latency. So if you look at this, when we throw this payload on the back of the robot sags for a small amount of time before it goes back up and starts and recovers its behavior. So there is a very small amount of adaptation time, because there are two things. First of all, the history should have enough information to predict, because if the payload lands, it's probably not enough to estimate what happened by just looking at one time step. So it needs some amount of history. So there's that inherent bottleneck on how fast it can adapt. And then there's a computational bottleneck. How fast can we run the network, which is supposed to adapt? So we do see in the friction experiment that if the slip is very extreme, that the robot has to preempt the slip. So the robot should know that it is going to enter a slippery surface. In those cases, it just falls. It is not able to react in the time frame.
Really cool. Thanks for elaborating. If I could get you to add to one more thing. On the parts where you forced, you said this, but I think I kind of missed it. How did you force the robot into the different gaits in order to make that energy comparison?
So if your question is on the plot on the left, how do I get the smooth? Okay, so we use an MPC based implementation. So there is a paper from the MIT Mini Cheetah group on convex MPC. So we used that, and that method lets you specify a gait pattern. So you can specify the contact sequence, and then it just walks at whatever speed you command. So we use that to generate this plot.
Cool, thanks.
So you will also notice that the stars are lower than the curves at the top. This is because we are explicitly optimizing for energy. So our energy will be lower, but in the MPC implementation we use, and which is also common practice, that the swing motion is usually predefined. The way the robot will swing its leg to get to a point is predefined, but we're learning all of that. We're learning everything from scratch. We just have a policy which is working at 100 hertz, and that learns everything. Okay, so I'd just like to conclude with 3 things which we considered as axiomatic in our work, and we have tried to build in our solution of legged locomotion. So the first is energy efficiency. So from the very beginning, we treated that as the only constraint, as opposed to any predefined foot motion or gait pattern or any such thing, because that is a practical constraint which is very relevant for mechanical systems like legged robots. The second thing we wanted was that we did not want to have any pre-programmed gaits. So we wanted gaits as the output of our learning system and not the input of our learning system. And lastly, we want rapid adaptation to varying terrains beyond what it has seen before, because in the lifetime of the robot, it is going to see situations and scenarios that it has never encountered before. And we need this ability to adapt to be able to have a robust deployment in the wild. Thank you. And if there are any more questions, I'm happy to take them.
Great talk, Ashish. Yeah, first applause in a year and a half, I guess.
So Tom, you can unmute, and I think you raised your hand. You can unmute and ask a question if you have.
You should be able to, well, other people were able to.
I have a question. So you use extrinsic vector.
You can just speak without that.
So you use an extrinsic vector as the eight-dimensional vector as an input to the base policy, right?
Mm-hmm.
Is that the common approach in legged locomotion, or you came up with that? Like you guys came up with that?
I mean, the more generally in deep learning, it is common to have a series of things chained together, because that kind of a compositionality very naturally falls out of the deep learning framework. So in this is more general in deep learning, specifically to legged locomotion. I mean, that's where I borrowed the idea from. I haven't paid a very close look to if people have taken additional inputs to base policy or not. But I think this idea has been around because it very naturally falls out in the deep learning framework, because everything is compositional. You just chain the gradients and you can train everything jointly.
May I ask a question?
Mm-hmm.
So I remember that I remember one scene that, for example, for dog or cats, when they are running, the rear leg will fit exactly the foot of his front foot. So the rear foot will step exactly onto the trace of its front foot. So do you mimic this pattern, or do you because from the video you mimic this pattern. You don't have
Yeah.
your rear foot step exactly onto the trace of the front foot. So
Yeah, that is correct. That happens at a high speed trot. So it's called a fast trot. So if you're trotting at a high speed, then you see that happening where the rear foot is tracking the front foot. But we actually we use like from this curve, we could have probably trained it for even higher and still gotten to the trot result, and then maybe we would see that behavior. But in the speeds that we did try, we did not see that. But that doesn't happen at all gaits.
okay.
Hi, so can I ask the question? So I was not allowed to unmute myself on my phone, but so I joined with my iPad now. Yeah, so my question is on the extrinsic vector that you train. So it's only like 8-dimensional, so it's really small. So so you did present like these 2 slides where you looked at like 2 of the values. So were you able to interpret the extrinsic vector in say like a more comprehensive fashion?
In a more what fashion?
So like did you like look at it like more comprehensively to see like what each one of them represent?
So we did look at that, and from those we picked up the ones which changed the most. But one thing to note is that this is a latent, so it's not directly interpretable, but there are other ways you can interpret it. You could have a readout function out of it to see how accurately it's recreating some of the mass values and so on. You could also do like a principal component analysis and so on, but each of these are lossy, or they add some information on top of the exact thing. So for the purposes of this presentation, I just chose to show the raw value to show that the extrinsics, or this which is supposed to capture the environment, is reacting to a change in the environment. So that's what we decided to show, but you could do more analysis to figure out what is this extrinsics actually showing. Do like more use the standard tools in interpretability to get a sense of what is exactly happening.
Thank you. So I have a follow-up question on that. So like 8 is really a small number, so especially considering how complex the environment can be. So have you tried to use, say, like a larger vector, or like what is the effect of using larger vectors? Like, why do you think 8 is appropriate here?
Yeah, so we started off by using 16 numbers, so the 16-dimensional extrinsics vector, and there is a trade-off. So the larger the extrinsics vector is, the more error we will accrue in the regression task. So when we try to regress in the second phase, and this also makes sense because if I make it very large, then in the first phase, the environment factor encoder can copy everything as is. So forcing it to actually be small will force the entire system to learn more general recovery behaviors, as opposed to overfitting to the exact friction and terrain height. We started off by 16, and the regression loss was high. So then we moved to 8 to see if that makes a difference. So, and then that did. So, but you're right. So the 8 might not be completely optimal. It's possible that 10 was the more optimal, or maybe we can go down all the way to 6. So we didn't do that analysis on each of these.
Thank you.
Do you think the extrinsic vector is doing the job for you?
I think, yeah. So in the analysis of the adaptation module, I think we see that once it slips, this is roughly where it slips. We see the extrinsic vector does do it. And then we also see that the recovery happens after that. We have another example where, let me just play this video in case you joined us. So we see that the robot starts slipping. And once it slips, and we see the change in the extrinsics value. So I'm at the bottom row, I'm just plotting the extrinsics value, and the top 2 are just the gait and torque profile of the robot. And we see that once it starts slipping, the extrinsics continues to capture the fact that something has changed, and then it recovers accordingly. We have another example, which is a payload throw. So we can toss a 5 kg of weight on the back of the robot, and we see that it gets disbalanced and then continues walking. We can see it in slow motion. You notice that when the payload lands on the back of the robot actually goes down, continues walking for a while, and then if you focus on the green dots, you'll see that it goes back up. And we can again analyze it in a similar way. The moment the weight lands, we see there is a change in the torque profile, in the gait profile, and then the extrinsics change their values to actually capture what is going on. So these are two separate extrinsic values than the ones that I plotted in the previous one. So these ones happen to capture mass, the previous ones happen to capture something about friction. And I think the true test of this lies in like the method working. So we literally have a comparison where we just switch off the adaptation module. So we have this everything same. We may run the adaptation module for the first time step and then freeze everything. And in this, you can see that this is the top is with RMA and it's an 8 kg payload. So this is roughly 70% of the body weight of the robot. And the recommended payload is 3 kg from the manufacturer. And you see that when we switch off the adaptation module, since the weight is in the front of the robot, it changes the mass and center of mass and everything, and the robot is not able to adapt to it.
One follow-up question is, you could have very well used like a different set of extrinsic vectors. So how difficult was it to come up, okay, this set of extrinsic vectors work well?
Sorry, I didn't follow. We could have used a different, what?
Different set of extrinsic, because you know.
Oh, you mean, so if I understand this correctly, you mean the one on the left?
Yeah.
So I just tried when making this list of environment factors to put in the extrinsics, the one thing which I took, the two things to that. So first of all, I tried to, whatever variations were there in the system or whatever I could vary in the system was an exhaustive list. But of those, what could be estimated from proprioception are the ones I included here, because not everything can be estimated from proprioception. If there's a gap in while you're walking and there's like a pothole or a gap on the floor, that to estimate from proprioception, you first have to fall inside it to figure out that something happened. So that cannot be estimated well enough. So if we included that, for example, that wouldn't work. So I limited it to the things which were estimatable from proprioception.
Okay.
One follow-up on that, based on these particular features that you've considered for the extrinsic vector, are there any cases where the robot fails? Like, are there any cases in any terrains where it tries to walk, but then it struggles and fails?
Yeah, so there are, so one are the obvious ones. If there's like a very sharp step, then the robot fails, because after it crosses a certain threshold, it's very difficult to recover. Or if it has to go up a long step, it cannot, because it needs, I think, a very long, we would have to train for it because it hasn't seen that height of something in simulation. The other setup is the friction one. So if the friction is very sharp, so for example, if there is the robot is going downhill and the friction is very sharp, it needs to preempt the friction to be able to successfully walk there. So these are the primary failure cases that we saw.
Okay.
Since we're talking about the sort of the adaptation module, I actually had maybe a provocative question about this. So, so how confident are you that this cannot just be replaced with like let's say like an end-to-end LSTM policy? Or maybe another way to put this question is, well, what would you do if you for some reason did not have the ground truth parameters, right? So like maybe let's say you collected a lot of data from a lot of different robots in a lot of different environments, but you collected them in the real world, so you don't have the estimated state and you have nothing to regress on. So how would you train the adaptation module then if you don't have this ground truth signal?
So I think that is actually a very good question. So if you think about it, that gets at two things. So one is a more practical consideration of, let's say, even in simulation, if I could not access them. The other consideration is in the real world, once the system is deployed, how can we continue improving? Because in that point, we don't actually have access to any of these. So how do we continue improving in the real world? And that's a research problem in itself. Continually learning and improving these systems without actually damaging the hardware. So, but to answer the more practical part of the question, that if we did not, one thing we could have tried and we did try was directly training from the history of 50 to predict an action. So we found two problems with that. So if you notice, we don't actually have any predefined leg motions or trajectories or gaits. So the gaits that it was converging to were very unnatural. And that is possible because the longer history it has, the more chances it has to overfit to the specifics of the simulation. So having this bottleneck here and the decoupled training has two benefits. So having this bottleneck here first allows us to easily get to nice behaviors. And
so, by predict the action, you mean you would train it with the PPO or like whatever you were using for your RL, or you would train it with the supervised learning loss?
No, I'll train it with RL. I'll keep everything the same. I'll just change the architecture to what you suggested. So I'll do that, but we did that, and the gait were very unnatural because it has more ways to overfit to the simulation. So this compression and only looking at the current state helped it to have nice behaviors. But another benefit of this decoupling is that this asynchronous deployment that you saw. So if we trained everything at 100 Hertz, and let's say part of it was only able to run at 10 Hertz, we would see a degradation in performance.
You kept everything the same, and you would just change the objective for the adaptation module. So you would keep the compression and the different Hertz thing.
Yeah, but then even if I trained this, let's say I trained phase 2 directly.
Yeah.
Right. That's your question, right?
Yeah, that's right.
Yeah. So even if I did that, the adaptation module at deployment now needs to run at 100 Hertz because there is no guarantee that this is not changing at 100 Hertz.
Okay.
Yeah. So initially, I also had a center of mass velocity in here. So the Z was changing at 100 Hertz. And I tried the policy in the real robot and it did not work at all.
Yeah, that's really interesting.
I would also just like to show this setup of the robot. This is my living room, my bedroom, and you can see that the robot is where I'm sitting right now. And this has been the setup that we've used to work throughout the pandemic. So now both of us share a room. Yeah.
Any other questions from the audience? And again, feel free to just unmute yourself.
Hey, I have a question. The higher level philosophical question, right? So I really like the idea of like how you were able to do so many things in simulation. So I wonder if you think this paradigm of like having a very good simulator that's able to allow you to train and also like train the adaptation module all inside a simulator, and then just do direct sim to real transfer is able to solve other like robotics tasks. For example, maybe like manipulation things. Like, do you think, like how scalable do you think this general paradigm is able to do?
If I had to just linearly extrapolate the rate of progress in simulations, like the soft simulations we have are getting better. They're getting a lot more visually realistic, a lot faster. And given the series of papers we have had from Sim to Real, which do a reasonably good job at doing it, I'm likely to believe that they're going to solve a reasonable chunk of the problem. But I think regardless of what we start with, we do want our systems to have this ability to actually learn in the real world itself, which is also what someone else asked earlier. And I think that is going to be important to have like reliable systems. We can always train for something and then put it in that exact setup and then try to see what happens. But if the robot fails, there's no recourse. So we would want systems which always learn in that's going to go there regardless of how close simulations get us to solving some of these tasks.
Thank you. Yeah, just final follow-up clarification question. What's the reward function you used in this project? I don't think you mentioned.
So the reward function we used are, so we have the task rewards. So the task rewards are, the robot has to move forward at a particular speed. The robot should maintain its orientation as upright. And it should not have any yaw in the sideways direction. So it should be walking forward and in an upright position. So those are the task rewards. We also have smoothness rewards and energy rewards. So we minimize the physical energy. So we compute how much energy is being consumed and we just penalize that. We also penalize the amount of delta torque or the jerk that we see, or encourage smoothness. So if the robot is changing torques very frequently, that will damage the motor. So we penalize that as well. And then there is a ground impact. So if the robot is stomping its feet very hard, we penalize that as well. So all of these hardware constraints is what we go for, as opposed to problem constraints. So for example, we don't constrain that the robot should have a specific clearance. We don't impose any gates or any such thing, but anything that will damage the hardware, we try to put it in the reward function. But in the follow-up work that I showed, we actually show that if we get rid of most of these terms and only have the task rewards, if we only have the task rewards and just along with those task rewards, like keeping upright and moving forward, we just minimize energy consumption. That is also sufficient to get the behaviors that we saw. So we found this in the, when we were trying to compare it to how researchers in biomechanics have approached this problem of getting a reasonable walking behavior.
Great.
Yeah, I think
Thank you.
that would be super interesting to provide the different task rewards like speed or stability or something that could be governed by like a vision system based on like some semantic segmentation or something of the scenery. So you can say, okay, there's something that I don't recognize that what's coming up, or a patch of grass, like go into stability mode. And then if you provided the kind of like the desired signal into, like in the original training, you said, oh, I'm going to penalize energy consumption. So like when you're training the network in simulation, maybe it would learn to the policy would learn to kind of incorporate sort of higher order commands for like how it should behave.
I am in 100% agreement of that I think right now we have a policy, we give it a velocity and it changes gait, but we would ideally like to automate that as well, because the robot should care about it. So the task should be go from here to here as fast as possible. And then it changes its speed and gait and everything as it tries to cross that path in the most safest way possible. And I completely agree that system can sit over this system and can also be trained in simulation. And I'm actually very interested in that direction. That's an excellent point.
Yeah, that's really cool. Thank you.
Cool. Just a last, or I don't know if anybody has, but I have a last question. If you have a minute, we're technically over time, but so feel free to leave because we're this will probably be official at the end of the meeting. But oh, and by the way, I realize that you don't know who we are since we're shouting from our places, but this is Oleg. I don't know if you can see me in the little camera window. And,
yeah, I can.
Can you?
Yeah, I've enlarged the video so I can actually see. Yeah.
So you had this very interesting slide that you flashed for a second, which said A1 adaptation, no vision. So I'm really curious. So what about the no vision part? Why should there be no vision? How that vision back?
So we are actually sorry. Complete your question.
Well, it just feels like vision is important. What are your thoughts on vision?
Yeah. So I am from a vision lab, and I completely concur with that. But the point of writing that was to mention more like this work does not have vision, as opposed to advocate for it, because we are trying to follow up this work with a version which has vision, because I think vision is important for two setups. So the first are critical setups, like if there's a hole in the ground, only a visual sensor can actually preempt that. And then there are non-critical setups. So in legged robotics, the biggest problem are the motors. So every time the robot walks and the leg hits the ground, the motor goes through some amount of impact. So we would want to minimize that impact, and vision can let us do that, because if the robot has to climb stairs by hitting the stairs first every single time, that is going to shorten the life of the robot. So I am all in favor of having a vision camera. And when I said no vision, I guess I was just trying to mention that this work has no vision. But yes, I'm completely in agreement with you.
I understand that, but I don't think that you were advocating for that way. I guess like the big question would be, well, I mean, you're training all of this in simulation, right? So none of what you just told us about would work if you wanted to learn vision. So I guess, I don't know, do you think it's even possible? It seems extremely hard.
It's not extremely hard. We have some ongoing work and some simulation results where it is able to come up with very interesting behaviors when we train it from scratch and with visual input in simulation. And we are trying to put it on the real robot. For this work, I think there are two things. We wanted to first understand the system, understand the current limitations and capabilities before we jump to a more higher dimensional sensor, which is perception or vision. But we also felt that this ability to adapt is going to be critical even if we have onboard vision. So this felt like something that had to be done. Yeah, but yes, I don't think it's like impossible or difficult. Or I think it falls in the same framework.
So you're saying you would just do sim to real basically from
yes for vision. Yes, I mean I'll try and let's see how it goes. But I think there are yes. But the hope is that some parts should work. There will be some calibration in some other parts, and then maybe there can be an automatic way to calibrate that as well. So there are lots of these ideas around in that space, but I haven't explored them fully just yet.
Makes sense. I hope that works. That would be amazing.
Yeah, it would. But that's a valid point. I think with vision, sim to real may or may not be challenging. We'll see. Yeah. Okay.
Any final? Well, I don't know if we have time for final questions. I guess actually, yeah, I'll just thank everybody for attendance. Thank Ashish for speaking. This was extremely interesting. Seems there was a lot of interest from the audience as well. And we'll have our next seminar next week, hopefully with snacks. So come in person for the.
Thanks everyone for attending, and thanks Ole for organizing this.
Thank you.